What are the advantages then of computational fluid dynamics? Well, key advantages are to do with the design of components. For example, we can use simulation-based design instead of build and test, and that can result in reduced effort when it comes to design. So it can reduce resources in terms of the amount of money that's being spent, in terms of the amount of material, in terms of even the sort of people that are required. Um, it can also mean that when we're getting data acquisition, which can be quite tough when it comes to experimental processes, that can be sort of made easier by using CFD. Another thing to note is that it's really useful because some scenarios just don't allow us to do experiments, to do controlled experiments. For example, if we're looking at something like a nuclear power plant or something like that, it's not easy, and it's not straightforward to go about doing tests in that sort of field of study. So that's something to think about and consider as well. Also means, for example, even if you're just looking at a Formula One car, then we could look at the behaviour, the flow behaviour of that Formula One car without having to build a model of that, which can be either expensive or could be quite intricate if we were doing a small scale model. Also, if we do a model for wind tunnel testing, then we could want to make some changes, and then that becomes expensive because we then need to potentially remake the model, or make changes to that model, which can be difficult. So CFD has advantages in that respect. Also is useful in terms of the exploration of physics. So CFD is actually used to look at the prediction of weather, and the behaviour of winds and currents. It's also used to look at our atmosphere and the planet's atmosphere, and even to look at the evolution of stars, so how stars have formed and how they grow and change. Um, and the details of what we can do in that respect are limited largely just by the computational resources that are available, and rather than the actual accuracy of the physics. Why do we use CFD? Why is it quite important that we do use it rather than just doing hand calculations? Well, almost all engineering flows are turbulent, and we can get really quite complex flow structures, and they can even be quite random flow structures. So measurements and experiments are not always sort of either not possible or potentially not feasible, and that means that we can use CFD for situations where either we have a really complex flow happening, or we have a highly turbulent flow. So, for example, if we're looking at turbo machinery, we can have quite a lot of turbulence in there. If we're looking at supersonic flow, then we've got the complexities of things like shock waves that we need to consider. So, CFD can be a really useful tool if it's used properly. That brings us on to some of the challenges of CFD. So challenges of CFD, first of all, there is a cost associated with CFD, and that is in terms of not only the software. So if you wanted to buy, for example, Fluent, then the license for that's going to cost a lot of money. Also, computational resources, so a lot of computing power, access to computing power in order to be able to run our simulations. And we also need people that are able to actually run the simulations as well. With CFD, there can be quite a steep learning curve. I think a lot of people think it's straightforward, pick and click, but if you want to really accurately model a simulation, there's a lot of things that need to be considered, from meshing through to the correct turbulence model, the correct solver. So it does take a lot of experience, and it is quite it's definitely a skill that has to be developed. It's not something that can just be easily picked up and done without any sort of prior knowledge. Another challenge of using CFD is what we call verification or validation. So we need to make sure that our results are reasonable and are correct. Because a lot of CFD simulations will give you an answer, but that doesn't necessarily mean that it's the right answer. It will only be the right answer if it's set up properly. So we need to make sure that our CFD simulations are set up in a way that is giving realistic results. We do that quite often by comparing our results with experimental results, or even with analytical results sometimes. So there is a degree of uncertainty when it comes to CFD. For example, if we're looking at turbulence models, they are just models, mathematical models of the flow, so they're not going to be 100% accurate. There is a degree of uncertainty in there. But usually that's something that we're able to deal with. Another challenge is that it's a field that's evolving, and been growing and evolving quite fast, particularly with the increase in the availability of high-speed computing. So it is quite a fast growing area, and therefore requires that we keep on top of the computing sort of side of things, and also looking at the mathematical side of things, and the new models that are being implemented and are being developed. So CFD codes, another challenge that's associated with CFD codes is that a lot of CFD codes or CFD packages or software are designed for representation of specific types of flow problem. So we need to be able to pick our models, our CFD flow models, in order to accurately represent or accurately model the flow. For example, there are different flow models for viscous flow compared with unviscous flow, with turbulent versus laminar flow, with compressible versus incompressible flow. Single and multi-phase flows have different models that we can potentially use. With the effects of energy and things, whether how important that is, we need to assess that. So there's a lot of different sort of things to do with flow physics that we need to understand about the flow problem in order to accurately set the simulation up. There's also things like there can even be chemical reactions or effects like surface tension that can come into play. So some codes are designed, for example, specifically to look at turbulent flows that are incompressible and are not so good for things like compressible flows, or maybe not so good for multi-phase flows, or not so good at chemical reactions, or potentially they are very good at chemical reactions but not very good at multi-phase flows. So we need to understand the physics of the problem in order to get the right flow models in place.